You should not exist. I don't mean that philosophically, I mean it physically. According to the laws of physics as we understand them, the Standard Model, quantum field theory, the most precisely tested framework in the history of science, the universe should have destroyed itself about 1 second after it was born. Every particle of matter that was created in the Big Bang should have been accompanied by an identical particle of antimatter, and within moments, every electron should have found a positron, every quark should have found an antiquark, and they should have annihilated each other in a cataclysmic flash of gamma radiation. The result would have been a universe of pure light. No atoms, no molecules, no stars, no planets, no you, no me. Nothing but an expanding fog of photons cooling toward absolute zero for all eternity. That didn't happen, obviously. You're sitting there, I'm standing here. The universe is full of matter, about 10 to the 80th atoms in the observable universe, roughly 5% of the total energy budget, and almost no antimatter. Somehow, in the first fraction of a second after the Big Bang, something tipped the scales. Something gave matter the tiniest edge over antimatter. And that tiny edge is why everything exists. My name is Leonard Susskind. I'm a theoretical physicist at Stanford, and I've spent over 50 years thinking about particle physics, cosmology, and the fundamental laws that govern the universe. And I can tell you that the mystery of where the antimatter went, or more precisely, why there's any matter left at all, is one of the deepest unsolved problems in physics. We know approximately what must have happened. We don't know how, and the gap between those two statements keeps me up at night. Let me show you why, and I'm going to be precise about this. Start with what antimatter actually is, because the popular picture is misleading. People hear antimatter and they think of some exotic, dangerous substance, the stuff from Star Trek or Dan Brown novels. But antimatter is not exotic, it's mundane. Every particle in the Standard Model has an antiparticle with the same mass, the same spin, but opposite charge and opposite quantum numbers. The electron has the positron, the proton has the antiproton, the neutrino has the antineutrino. Paul Dirac predicted the existence of the positron in 1928, purely from the mathematics of his relativistic equation for the electron. And Carl Anderson discovered it in a cloud chamber in 1932. It was one of the most stunning confirmations of theoretical physics in history. A particle predicted by an equation found in nature exactly as described. Now here's the thing about antimatter that matters for our story. When a particle meets its antiparticle, they annihilate completely. Their combined mass is converted entirely into energy, according to Einstein's E equals mc squared. An electron has a mass of about 9.1 times 10 to the minus 31 kilograms. When it meets a positron, both vanish and produce two gamma-ray photons, each with an energy of 511 kiloelectron volts. That's 100% mass-to-energy conversion. For comparison, nuclear fission converts about 0.1% of mass to energy. Nuclear fusion converts about 0.7%. Antimatter annihilation is 100%. It's the most efficient energy release permitted by the laws of physics. And the process works in reverse. If you have enough energy, a sufficiently hot, dense environment, photons can spontaneously create particle-antiparticle pairs. This is pair production, and it happens routinely in particle accelerators. At CERN's Large Hadron Collider, every proton-proton collision at 13 tera-electron volts of center of mass energy produces sprays of particles and antiparticles in roughly equal numbers. The laws of physics, as we understand them, treat matter and antimatter with near-perfect symmetry. Create a particle, you create its antiparticle. Destroy them, you get light. The books balance. Now, rewind to the Big Bang. In the first microsecond, the first millionth of a second, the universe was unimaginably hot. Temperatures above 10 to the 13 Kelvin, roughly 1 trillion degrees. At those temperatures, the thermal energy of the environment exceeds the rest mass energy of protons and neutrons, which is about 938 mega-electron volts. That means the universe was a seething plasma of quarks, antiquarks, gluons, electrons, positrons, neutrinos, antineutrinos, photons, everything the Standard Model permits, all being created and annihilated in a frenzy of pair production and pair annihilation, all in thermal equilibrium. And at that moment, there should have been exactly equal numbers of quarks and antiquarks, exactly equal numbers of electrons and positrons. The symmetry of the underlying physics demands it. Every process that creates a quark also creates an antiquark. Every process that destroys a quark also destroys an antiquark. The ledger should be perfectly balanced. But it wasn't. And we know it wasn't because we can measure the imbalance. Here's how. The cosmic microwave background, the afterglow of the Big Bang, first detected by Arno Penzias and Robert Wilson in 1965, mapped with extraordinary precision by the WMAP satellite in 2003 and the Planck satellite in 2015, tells us the ratio of photons to baryons in the universe. There are about 410 cosmic microwave background photons per cubic centimeter of space, and about 2.5 times 10 to the minus 7 baryons per cubic centimeter. The ratio is roughly 1.6 billion photons for every baryon. Those photons are the remnants of all the annihilation, all the matter and antimatter that did find each other and destroy each other. The baryons, the protons and neutrons that make up you, me, the Earth, every star in every galaxy, are the tiny residue that was left over. Let me be very precise about this. For every billion antiquarks in the early universe, there were 1 billion and 1 quarks. The excess was about 1 part in a billion, 1 extra quark for every billion quark-antiquark pairs. The billion pairs annihilated into photons. The 1 leftover quark became part of the matter we see today. That's not a typo. 1 part in a billion. The entire visible universe, every atom in every galaxy, every star, every planet, every grain of sand, every cell in your body exists because of an imbalance of 1 part in 10 to the 9th. If the universe had been perfectly symmetric, there would be nothing, just light. We owe our existence to the smallest asymmetry imaginable. So where did that asymmetry come from? This is the problem of baryogenesis. And it's been open since Andrei Sakharov, yes, the Soviet physicist who also designed hydrogen bombs and later became a dissident and Nobel Peace Prize laureate, laid out the conditions in 1967. Sakharov showed that to generate a matter-antimatter asymmetry from an initially symmetric universe, you need exactly 3 conditions. First, there must exist processes that violate baryon number conservation, processes where the total number of baryons can change. Second, there must be violations of C symmetry and CP symmetry, the symmetries that relate matter to antimatter. Third, these processes must occur out of thermal equilibrium, because in equilibrium, every process is exactly balanced by its reverse, and no asymmetry can build up. These are called the Sakharov conditions, and they are necessary and sufficient. If any one of them is missing, you can't generate the asymmetry. All three must be satisfied. Let me walk through each one. Baryon number violation. In the standard model, baryon number is conserved in every interaction you've ever seen. Every reaction in every chemistry textbook, every nuclear reaction, every particle collision at the LHC, baryon number is preserved. But here's the remarkable thing. The standard model actually does violate baryon number through a subtle quantum effect called a Sphaleron process. This was worked out by Gerard 't Hooft in 1976 and later by Franz Klinkhammer and Nick Manton in 1984. At ordinary temperatures, the rate of Sphaleron processes is suppressed by an exponential factor, roughly e to the minus 4 pi over alpha weak, which works out to about 10 to the minus 170. That is so small, it has never happened once in the history of the observable universe at room temperature. But at temperatures above the electroweak scale, above about 160 GeV, or roughly 10 to the 15 Kelvin, sphalerons become rapid. They happen all the time. In the early universe, before the electroweak phase transition, baryon number was being violated constantly. Sakharov condition 1, satisfied, CP violation. This is where it gets interesting and where it gets heartbreaking. CP symmetry says that if you take a physical process, replace every particle with its antiparticle, that's C for charge conjugation, and then mirror the spatial coordinates, that's P for parity, you should get the same physics. For decades, people believed CP was an exact symmetry. Then in 1964, James Cronin and Val Fitch discovered CP violation in the decay of neutral kaons at Brookhaven National Laboratory. They found that the long-lived neutral kaon, which should decay only into 3 pions if CP is conserved, occasionally decayed into 2 pions. The effect was tiny, about 2 parts in 1,000, but it was real. It was a Nobel Prize in 1980. Since then, CP violation has been studied extensively. The Babar experiment at SLAC, which ran from 1999 to 2008, and the Bell experiment at KEK in Japan measured CP violation in the B meson system, confirming that the Kabibo-Kobayashi-Maskawa matrix, the matrix that describes quark mixing, predicted by Makoto Kobayashi and Toshihide Maskawa in 1973, contains a complex phase that is the source of CP violation in the standard model. This earned Kobayashi and Maskawa the Nobel Prize in 2008. So the standard model has CP violation. Sakharov condition 2, satisfied, in principle. Now here's where it gets ugly. The amount of CP violation in the standard model is far, far too small to explain the observed baryon asymmetry. When you calculate the baryon to photon ratio that the standard model's CP violation can produce, using the CKM phase and the known quark masses and mixing angles, you get a number of order 10 to the minus 18. The observed ratio is about 6 times 10 to the minus 10. The standard model falls short by 8 or 9 orders of magnitude, 1 billion times too little. The CP violation is there, but it's hopelessly inadequate. And it gets worse. The third Sakharov condition, departure from thermal equilibrium, was supposed to be provided by the electroweak phase transition. In the early universe, as temperatures dropped below about 160 GeV, The Higgs field acquired its vacuum expectation value of 246 GeV, and the W and Z bosons gained their masses. If this transition was strongly first order, like water freezing, with bubbles of the new phase nucleating inside the old phase, it would provide exactly the kind of out-of-equilibrium dynamics that Sakharov requires. Beautiful idea. Doesn't work. We now know, thanks to lattice calculations done in the 1990s and confirmed many times since, that for a Higgs boson mass of about 125 GeV, the value measured at the LHC in 2012 by the ATLAS and CMS experiments, the electroweak phase transition is not first order. It's a smooth crossover, no bubbles, no sharp boundary, no dramatic departure from equilibrium. Sakharov condition 3, not satisfied, at least not in the standard model. So where does that leave us? The standard model of particle physics, the theory that correctly predicts the magnetic moment of the electron to 12 decimal places, the theory that predicted the Higgs boson decades before it was found, the theory that has survived every experimental test thrown at it for 50 years, cannot explain why you exist. It gets the CP violation wrong by a factor of 1 billion. It gets the phase transition wrong qualitatively. The most successful theory in the history of physics fails at the most basic question: why is there something rather than nothing? Think about that for a second. This means there must be new physics beyond the standard model. Not might be, must be. The existence of matter in the universe is proof, experimental, observational, irrefutable proof that the standard model is incomplete. Not wrong, incomplete. There are particles we haven't discovered, or symmetries we haven't identified, or interactions we haven't measured, that provided the additional CP violation and the out-of-equilibrium conditions that tipped the scales by 1 part in 1 billion. People have proposed many ideas. Let me tell you about a few and what's wrong with each of them. Leptogenesis. This is probably the most popular idea in the field today. The concept, developed by Masataka Fukugita and Tsutomu Yanagida in 1986, is that the asymmetry was generated not in the quark sector, but in the lepton sector, with heavy right-handed neutrinos. These hypothetical particles, with masses of perhaps 10 to the 10 to 10 to the 15 GeV, would have been produced in the early universe, decayed in a CP-violating way into leptons and antileptons with a slight imbalance, and then the Sphaleron processes I mentioned earlier would have converted part of that lepton asymmetry into a baryon asymmetry. It's elegant, it's economical, it connects to the fact that neutrinos have mass, which we've known since the Super Kamiokande experiment in 1998. The problem? The right-handed neutrinos, if they exist, have masses so high that we can't produce them in any accelerator. The LHC operates at 13 TeV. These neutrinos might be at 10 to the 10 GeV or higher, 1 million times beyond our reach. We can't test this directly. We can look for indirect signatures like particular patterns in the light neutrino masses and mixing angles, but it's circumstantial evidence at best. Electroweak baryogenesis with new physics. Maybe the electroweak phase transition was first order after all, not in the standard model, but in an extended version with additional Higgs bosons or new scalar particles. Supersymmetric models, 2 Higgs doublet models, and various other extensions can make the transition strongly first order and add new sources of CP violation. Some of these models predict electric dipole moments for the electron and neutron that are just below current experimental limits. The current bound on the electron's electric dipole moment, measured by the ACME collaboration in 2018, and updated by the Gilla group in 2023, is less than about 4.1 times 10 to the minus 30 electron centimeters. Many of these models predict values within a factor of 10 of that bound. So we might be close. But close in physics can mean decades of work. And so far, the electric dipole moment is consistent with zero, no signal. Affleck-Dine baryogenesis. Ian Affleck and Michael Dine proposed in 1985 that flat directions in the scalar potential of supersymmetric theories could store a large baryon number in the early universe, which later decays into the observed asymmetry. It's clever, and it works on paper. The problem is that it requires supersymmetry, and after decades of searching at the LHC, we have found no evidence for supersymmetric particles. The absence of superpartners below about 2 TeV, the current exclusion limits from ATLAS and CMS, doesn't rule out supersymmetry entirely, but it makes many of the simplest versions increasingly uncomfortable. Could I be wrong about the standard model being incomplete? Could there be some mechanism within the standard model itself that I'm missing? I've been wrong before, but this one is hard to see a way around. The numbers are unambiguous. The CP violation in the CKM matrix is measured. The Higgs mass is measured. The electroweak crossover is calculated on the lattice with controlled uncertainties. The baryon to photon ratio is measured from the cosmic microwave background to better than 1% precision by the Planck satellite. These aren't estimates or conjectures. These are hard numbers, and they don't match. Something is missing. Could the answer come from a completely unexpected direction? Something nobody has thought of? Absolutely. That's happened before in physics. Nobody expected parity violation before Li and Yang proposed it in 1956 and Wu confirmed it in 1957. Nobody expected CP violation before Cronin and Fitch found it. The universe has a long history of surprising us with symmetry violations that we didn't anticipate. And the baryon asymmetry problem might require an equally surprising answer. Let me tell you what I find most remarkable about all of this. The universe exists on a knife's edge. If the asymmetry had been zero, perfect symmetry between matter and antimatter, there would be nothing. If it had been much larger, say 1 part in 1,000 instead of 1 part in 1,000,000,000, the universe would look very different. The ratio of matter to radiation affects the formation of light elements in Big Bang nucleosynthesis, the growth of structure, the formation of galaxies. The 1 part in 1,000,000,000 asymmetry is not just any number, it's woven into the fabric of cosmological history. Change it, and you change everything. And we don't know where it came from. I've been doing physics for over 50 years, and there are problems that I've seen solved beautifully in my lifetime. The electroweak unification, the discovery of asymptotic freedom, the confirmation of the standard model piece by piece, culminating in the Higgs boson in 2012. But the baryon asymmetry, the question of why there is matter rather than nothing, remains stubbornly, frustratingly open. Some people find this frustrating. I find it wonderful, because it means the universe still has secrets. Not little secrets, like the mass of some undiscovered particle, a big secret. A secret about why anything exists at all. The 1 part in 1,000,000,000 that separates a universe full of galaxies and stars and people from a universe of empty light. That number is a message from physics we haven't decoded yet. Every atom in your body is evidence that the standard model is incomplete. You are, quite literally, proof that there is more to discover. When I was a young physicist in the 1960s, people talked about the final theory as though it were just around the corner. We'd unify the forces, understand the particles, and that would be that. I was naive enough to half believe it. 60 years later, the baryon asymmetry stands as one of the clearest signs that the final theory, if such a thing even exists, is far away. And I find that not discouraging, but thrilling. The deepest question isn't some abstract puzzle in mathematical physics. It's staring you in the face every time you look in a mirror. Why are you here? Why is anything here? The answer is hidden in a 1 part in a billion asymmetry that we don't understand. After all these decades, the universe can still surprise me with the simplest things. Thank you for listening.